Hello everybody, my name is Mr. McAllen and I'm going to be talking today about the unit circle, and I'll be talking about it as another way to compute trig values. I'm going to first start off with the way that we have been working with trig values in the past. For example, when you would get a value and you would be asked to find the sine of 135 degrees, some of you have been taught that if you recognize a reference angle for 135 degrees, so we draw the angle 135 degrees. You'd recognize the reference angle is 45. You would consider that to be a 45, 45, 90. And you would label the sides as being -1 because it's pointing to the left, 1 because it's pointing up, and root 2 would be the hypotenuse. That you would just write the trig ratio to be the opposite over the hypotenuse, which would be 1 over root 2, which would be later rationalized to root 2 over 2. When you came up against the ratio where it asked for the cosine of 90, we had a trig table that showed all of our quadrantal values. And for the sine, and for the cosine, and for the tangent, we would just follow the pattern of the trig values. So sine would alternate. It would go from 0 to 1 to 0 to -1 to 0, and cosine would vary from 1 to 0 to -1 to 0 to 1, and tangent would be 0 and undefined, and 0 and undefined, and 0. So you'd use that table for quadrantal values to figure out what the cosine of 90 was. The cosine of 90 in this table would be 1. And if you got the angle for the tangent of 30, you would again draw the angle, recognizing that the reference angle was 30 degrees, and you would label the triangle just like from our trig diagrams given on the SAT test. We would label this to be 2 and this to be root 3. We would label our vectors as being pointing up, pointing to the right, and our tangent ratio would be the opposite over the adjacent, which would rationalize to be root 3 over 3. Well, the way I propose today that we're going to work with trig values is by this other mechanism called the unit circle. Okay, so now I have a picture of the unit circle, and some of you may wonder, well, why the change to the unit circle? Why not do it the way we've been doing it? And there are a few reasons. I have 5 listed here. First of all, it's clever. Second of all, it captures everything, quadrantal angles and reference angles from 30, 45, and 60 degrees. It reinforces a Pythagorean identity. It reinforces the all students take calc acronym and vectors. And since sine and cosine are known as circular functions, why not use the unit circle? So I'm going to demonstrate over here on the right how we use it and how we label it. So the first thing we do is we just label the points on the quadrant lines. And remember, this is a unit circle, so that means that the radius is equal to 1. So the point here, the first point, would be at the point 1, 0. The point at the top at a 90-degree position would be 0, 1. The point at the left will be -1, 0. And the point down below at 270 degrees would be labeled 0, -1. With this being said, it's important to note that the coordinates have a certain makeup. The x-coordinate, x, y, the x-coordinate is the cosine of the angle theta, and the y value is the sine of the angle theta. If you look at your chart that we had from before, you would notice that the cosine of 0 degrees is 1. And the sine of 0 degrees is 0. And if we go back to the chart and we look at the quadrantal values, the sine of 0 degrees was 0, and the cosine of 0 degrees was 1, which reinforces that the coordinates on the unit circle are correct. So, moving back to the unit circle, and let me just tidy the drawing up a bit. When we go around the unit circle, we'll just start off the first angle here. I'll just label the angle. This will be 30 degrees. When we're at the point for 30 degrees, if you remember what the sine of 30 was and the cosine of 30, the sine of 30 or cosine of 30 was root 3 over 2, and the sine was 1/2. When we moved to 45 degrees, the sine was root 2 over 2, and the cosine was root 2 over 2, and the sine was root 2 over 2 as well. And when we move to the point where we're at 60 degrees, the cosine was 1/2, and the sine was root 3 over 2. Some important things to note with the coordinates here is that there's a progression that the point 1, this point at 1, 0 can also be thought of as a value of root 4 over 2, 0. And if you look at the pattern, you can see that the x values are moving from root 4 over 2 to root 3 over 2 to root 2 over 2 to root 1 over 2 to root 0 over 2. And you see a descending pattern for the x values as you go from 0 through 90 degrees. You see the alternative pattern, or the opposite pattern, occurring when you look at the y values. You start at 0, and then you go to root 1 over 2, root 2 over 2, root 3 over 2, and root 4 over 2, which is equal to 1 on the other side. Following this pattern is very easy to fill in all the other blanks. And I'm going to do that quickly because I don't want this video to take too much longer than 10 minutes. But the next angle is 120 degrees. And this point would be just the mirror image of the point at 60. It would be at -1 over 2, comma, root 3 over 2. At 135 degrees, the point would be negative root 2 over 2, comma, root 2 over 2. And at 150 degrees, which has a reference angle again of 30, this point would be root 3 over 2 negative, comma, 1 over 2. As we move around the unit circle, we've got to be careful of our coordinate values. All the coordinate values will be mirror images of the last. I'm going to change the ink color so that we can see that now we're in another quadrant. And I'm going to change this, so this now is going to be negative root 3 over 2, comma, negative 1/2. This point will be negative root 2 over 2, comma, root 2 over 2. And this point at, let me label these. This is 210 degrees. This is 225 degrees. This is 240 degrees. And this point would be looking straight above here. I can see my same exact point. I'm going to have negative 1/2, but now this is going to be negative root 3 over 2. And let me just erase that so it doesn't mess up the drawing. But you can see you can use lots of the symmetry around the table. If you know the first 5 values, those can help you build the rest of the table. We're going to just mark up the last 5, and then we're going to talk about a few of the interesting properties that these values have. So now we're at the angle 300 degrees. Let me change the ink color again. That will be, I used red, blue, green. Let's use black this time. And this point will be negative 1/2, positive 1/2, negative root 3 over 2, because the x value should be positive and the y value should be negative. That's at the angle 300 degrees. Now I'm at 315 degrees. I have the angle root 2 over 2, comma, negative root 2 over 2. And then the last point, I have the coordinates root 3 over 2, comma, negative 1/2. And that would be at 330 degrees. Now you might be wondering, how is this going to help you know all of your trig values? Well, once you draw this picture, the coordinates, the x-coordinate is the cosine ratio. The y-coordinate of every point is the sine ratio. If I zoom out, let's just work with one of our favorite identities. We know that the sine squared of theta and the cosine squared of theta, when you add them together after you square them, it should equal 1. And this is because we're working with a unit circle. If we try this out and we pick any point, let's say the cosine of 315 degrees, we'll square that value plus the sine of 315 degrees. We'll square that value. And if you look at the point for 315, you'll be plugging in the value for the cosine. It'll be root 2 over 2. We'll square that plus root 2 over 2. Negative, we'll square that. And when you square them, you end up getting 2 over 4 plus 2 over 4, and that equals 1. So this is just proof that at any point our unit circle or our Pythagorean identity will work. And in addition to that, we notice some other things that happen. Remember how we said that the sine ratio is the y-coordinate? Well, remember when we worked in earlier videos, we talked about an acronym called ASTC. In this quadrant, all trig ratios are positive, and I just want you to note that the x and the y coordinates are all positive in this quadrant. So what happens is all trig ratios would be positive there. In the sine quadrant, in quadrant 2, notice the x-coordinates are negative, but the y-coordinates are positive, because the y-coordinates represent the sine values. And the sine deals with the y quantity of the unit circle. People may wonder, okay, well, you've given me a way to remember the sine ratio and the cosine ratio, but how do I get the tangent ratio for any angle? Well, the tangent ratio is simply equal to, as we did with our identities, the sine quantity over the cosine quantity, and that would just be as easy as looking at the y-coordinate divided by the x-coordinate on your unit circle. So if I asked for the tangent of an angle, that would equal, let's say, the tangent of 30 degrees, I would just go to 30 degrees, and I would look at the y value, which is 1/2, divided by the, let me zoom out, divided by the x value, which is root 3 over 2, and you would end up getting 1 over root 3, or rationalized root 3 over 3. If I asked for, let's say, the secant of, let's say, 240 degrees, then you would go to the 240 degree mark, and you would do, you would look for 1 over the cosine of 240 degrees, which is the same as 1 over the x value at 240, which would be 1 over negative 1/2, which would equal negative 2. I hope this video has helped, and I would like to see, I would like to hear more comments that you have regarding the unit circle, and if there are any questions, please don't hesitate to comment. Thank you.